All right, welcome. Every single time you send an email or stream a movie or just, browse the web, you're tapping into this massive global system that honestly, it feels like magic. But it's not magic at all. It's actually a set of incredibly clever rules. So today we're going to pull back that curtain and really demystify the hidden infrastructure that makes our entire modern internet possible. So let's just start with a question that seems simple but is actually pretty profound. How does an email, or a photo, or any file for that matter, get from your screen to someone else's, maybe halfway across the planet, in literally the blink of an eye? I mean, think about that for a second. To answer that, we need to dive into the secret language that all computers use to talk to each other. Okay, so here's our game plan. First, we'll take a quick trip back to a world without connection. Then we'll get into the internet's universal rulebook, the thing that organizes all this digital chaos. After that, we'll look at a really interesting trade-off, speed versus reliability. And finally, we'll actually trace how your data makes its incredible journey. So let's set the scene. We're going back to the 1960s. And in the 1960s, computers were, well, they were huge, they were incredibly expensive, and they were also profoundly lonely. I want you to just picture these giant mainframe computers. Each one is from a different company, and each one basically speaks its own unique private language. So yeah, they were powerful, but they were total islands. Researchers couldn't just share data. They were constantly duplicating work, and progress was just crawling along. The big problem, the fundamental challenge, was incompatibility. So, to solve this mess, a project called ARPANET was born. And it started small, really small. In 1969, just 4 computers were connected. But the real breakthrough, the moment that changed everything, was in 1982. That's when this thing called TCP/IP was formalized. All of a sudden, there was a universal translator, a common language that would let any computer from any manufacturer speak to any other computer. It was a game changer. And by 1990, the original ARPANET experiment was pretty much over because its mission was complete. The internet, as we know it, had begun. Okay, so let's dig into that game-changing solution, TCP/IP. And it's important to know, it's not just one single thing. It's more like a whole suite of rules, a master blueprint for how everything talks to everything else. Right at the heart of TCP/IP is this idea of a protocol. And you can think of a protocol as just digital etiquette. Seriously, it's a set of rules that everyone agrees on beforehand, so that when one device sends a message, the other one can actually receive it and understand it perfectly. Without these protocols, the internet would just be, well, a bunch of noise. And this is really the core idea in action. It just doesn't matter what device you're using or where in the world you are. A brand new smartphone in Tokyo can have a perfect conversation with a 50-year-old server in Kansas, all because they've both agreed to follow the same master rulebook, TCP/IP. It truly is the internet's universal language. Okay, so you can imagine handling all this complexity is a huge task. So to manage it all, the designers of TCP/IP did something brilliant. They broke the problem down into smaller, manageable chunks. You can call them layers. The best way to think about it is like a mailroom, right? You've got one department that writes the letter, another one that puts it in a box, a third one slaps the address on it, and a fourth puts it on the right truck. Each layer has one and only one specific job to do. So as your data travels down through these layers, each one literally wraps it in a new digital envelope. It's a process called encapsulation. So the application layer creates your message, then the transport layer adds its info about reliability, then the internet layer adds the global address, and finally the link layer preps it for the local network. And the absolute genius of this system is that each layer only has to worry about its one job before passing the package down the line. This modular design is what makes the internet so incredibly flexible and scalable. So there you have it, 4 layers all working together in perfect harmony. And look, they're all super important, but we're about to zoom in on one of them in particular, the transport layer. Why? Because this is where a really fascinating and absolutely crucial decision gets made about every single piece of data you send. All right, let's focus on that transport layer, because it has to answer this fundamental question for everything you do online. Is it more important for this data to be perfectly reliable or for it to be lightning fast? And here's the kicker, you can't always have both. And this is where we meet the 2 main specialists of the transport layer, TCP and UDP. Think of TCP as the meticulous, careful one. It establishes a formal connection, and it guarantees that every single bit of data arrives perfectly in the right order. It even resends any little pieces that get lost along the way. UDP, on the other hand, is the sprinter. It's all about speed. It's a fire and forget system that just blasts data out as fast as it possibly can, with zero guarantees. So, how exactly does TCP pull off that reliability guarantee? Well, it uses something called a three-way handshake. Before a single byte of your actual data is sent, the two computers have this super quick, polite conversation. One says, "Hey, I'd like to connect." The other says, "Got it, I'm ready too." And the first one replies, "Great, let's do this." It's basically a formal agreement that says, "Okay, we are both ready, we're both listening, let the data transfer begin." And this, right here, is why TCP is the backbone for anything that has to be perfect. You just can't have a few words missing from an important email, right? Or a big corrupted spot in a family photo. For those kinds of things, we are more than willing to sacrifice a few milliseconds of speed to get 100% accuracy. But UDP, it's built for pure speed. This is what you're using for live video calls or online gaming. In those situations, a constant, fast stream of data is way more important than perfection. I mean, think about it. If a single pixel on your video call glitches for a fraction of a second, who really cares? It doesn't matter. The important thing is keeping that conversation going with as little lag as possible. Okay, so we've got our rules, we've got our layers. Now for the last piece of the puzzle. How does all this digital instruction manual, actually translate into data physically moving across wires and through the air? This is what it all boils down to at the lowest level. Your data, your email, your photo, whatever, it gets chopped up into these neat little packages called frames. And if you look, you can see it's basically a tiny digital parcel. It's got the to and from addresses, it's got the actual data inside, that's called the payload, and it's got this crucial little check at the very end to see if anything went wrong. And that error checking part, it is absolutely vital. I mean, as these packets are flying across the network at the speed of light, things can go wrong. You get static, interference, you name it. So these simple but totally brilliant techniques, like a parity check, are built right into the rules. They let the receiving computer instantly double-check if the data it just got is the exact same data that was sent. It's really one of the unsung heroes of our reliable digital world. And you know, this all points back to a core philosophy baked into the internet's design. It's called the end-to-end principle. The idea is to keep the network itself as simple or dumb as possible. Its only job is to move packets from A to B. That's it. All the smarts, all the intelligence lives at the edges, in your devices. And that seemingly simple idea was completely revolutionary. It meant that anyone could invent a new app or a new service without having to ask permission from the phone company or the network owners, and that is precisely why the internet has been able to innovate and grow so explosively. So there you have it. We've gone from these lonely, incompatible mainframes all the way to a global network governed by this elegant, layered rulebook. We've seen exactly how TCP/IP makes our connected world tick. But it leaves us with a pretty fascinating thought. The core rules we've been talking about, they were designed almost 50 years ago for a world that we would barely recognize today. So as we head into an age of AI, the Internet of Things, and who knows what else, you have to wonder, what will the rules of the next internet look like?